Welcome to this class on financial performance measurement. This is part 7 of this topic. Today we'll talk about internal rate of return, also defined as IRR, and net present value ratio, also defined as NPVR. So the outline today will require the analysis of internal rate of return, IRR, and net present value ratio, NPVR. So let's start from the internal rate of return. The internal rate of return is said in a simple way, the rate of return of a project given the structure of its cash flows, and then we'll see what this means, and we'll enter into more details about the calculation of this indicator. So in particular, we can see the IRR is an indicator that has two meanings. The first one is a formal meaning, because from a formal point of view, is the discount rate at which the NPV is equal to 0. So in order to calculate it, as we'll see, you have to set the NPV equal to 0 by changing the discount rate, and the IRR will be exactly that discount rate that will make the NPV equal to 0. That is exactly the same thing as saying that is the discount rate that makes the present value of the outflows equal to the present value of the inflows, because we know that when the NPV is equal to 0, this means that the present value of the outflows is equal to the present value of inflows. So the two conditions are completely equivalent from an algebraic point of view. The other meaning that I was anticipating before is the meaning of rate of return of the project. And this is a very important interpretation of the IRR, because it provides a synthetic indication of the rate of return that a project is providing to the investors, and is for the NPV, also in this case, the IRR can be calculated in the perspective of the total investors or of the equity. What is important to remark, however, is that the IRR per se is not a specific meaning, in the sense that a 10%, a 15% of rate of return does not necessarily mean that the project is convenient. So by definition, a positive IRR does not necessarily imply that the project is valuable for investors. So in order to apply the IRR as a method, as we'll discuss in this class and in the next ones, we have to find some criteria that allow us to say whether 10% or 50% IRR is sufficient or not to say that the project is convenient or not. So the result that we get will be after to be interpreted in the light of some criterion about the appropriate rate of return that I should expect from a project. So this is the formula of the internal rate of return, consistent with the definition that we have just provided. So the formula that you observe here is again the formula of the NPV. So this is not different from the formula of the NPV that we have seen in the previous class. So again, we have the summation for t going from 0 to n, where t is the timing of each cash flow, 0 is the moment of the initial investment, and then is the last year of the life of a project. So summation of operating cash flows at time t, and here we're talking about internal rate of return for the total investment. Then we'll discuss what is the difference when we'll work on the equity side. Divided by 1 plus r star, and now I will explain the meaning of this star here, raised to t. So this formula is exactly the same as the NPV, with a difference about the star of R. But the main important difference is that here what we want to calculate is not the NPV, but it's exactly R star. That is, as you can see in the slide, our internal rate of return. So the R star or IRR is our unknown variable, that is calculated by setting the NPV equal to 0. So we are calculating here the formula of the NPV. We are equating it to 0, so that the NPV is known and is equal to 0. And we want to know what is that particular discount rate that makes the NPV equal to 0. And this is exactly by definition of the IRR. So in order to calculate the IRR, we have to solve this equation by R star. Once that R star has been calculated, this is exactly the indicators we are looking for in this internal rate of return. This formula can be also interpreted from a graphical point of view. And what we can see here is that the IRR is exactly the point where the NPV curve intersects the x-axis in this graph. Again, this is a graph where that we have already seen in the previous class. It's a graph where on the y-axis we have the NPV and the x-axis we have the discount rate. We have already explained that the NPV is a decreasing function of the discount rate. So that for the whole interval of the possible discount rates we consider here, the NPV will be monotonically decreasing. And there will be some discount rates for which the NPV is positive and some other discount rates for which the NPV is negative. And there is a particular discount rate that is the value for which the NPV intersects the x-axis. That is exactly what we are looking for, that is the IRR. So this graphical definition is a consequence of the analytic definition that we gave in the previous formula. In the previous formula, we said that the IRR was the discount rate that made the NPV equal to 0. So from a graphical point of view, this means that the IRR is the point where the NPV intersects the x-axis. So it's this graphical definition is just a consequence of the analytical definition that we gave in the previous slide. So now we have all the analytic tools to interpret in a more comprehensive way the meaning of this graph. So what we said in last class is that when NPV was higher than 0, this happened for the discount rate at the left of the intersection point. The project was convenient. Instead, on the right of the intersection point, for all the discount rates that were here, so higher than the IRR, the NPV was negative, so the project is not convenient. So we already had a rule that said that when the NPV was positive, the project was convenient, and when the NPV was negative, the project was not convenient. Here we can express the same rule as a function of the IRR, and in particular, what we can see is the following. If the discount rate we adopt for the NPV is lower than the IRR, that is also if the IRR is higher than discount rate that we use for the net present value, the project is convenient and the NPV is positive. On the contrary, when the IRR is lower than the discount rate, or an alternative, the discount rate is higher than IRR, the NPV will be negative and therefore the project will be not convenient. So we have a new rule to say whether the project is convenient or not, that is based on IRR. And the rule is that if the IRR is higher than the discount rate, the project is convenient. If the IRR is lower than the discount rate, the project is not convenient. And we can simply observe in this graph that this new rule based on the IRR is totally equivalent to the rule that we had defined for NPV. In fact, when IRR is higher than the discount rate, we are in this part of the graph, so the NPV is positive, and both the IRR rule and the NPV rule suggest that the project should be realized. On the contrary, when the IRR is lower than discount rates, this means that we are in this particular area of the graph where the NPV is negative, and so we know that the project is not convenient. So again, when the IRR is lower than then so of the discount rate and the NPV is negative, the project is not convenient, and both rules are suggesting the same result. So in general, as we'll discuss in a moment, IRR and NPV will provide the same indications about the convenience of a project, even though there are some specific cases where this does not happen, and so we have to be careful in the use of IRR as a valuation tool for a project. However, a final remark is important here to conclude the discussion on this slide. The fact that the IRR is positive per se is not a particular an insightful meaning for a project. Does not imply anything about the convenience of the project. Because, for example, it could happen that the IRR is around 13%, as in this case, but the discount rate for this project is 20%. So in this case, the IRR will be lower than discount rate, and the project will be not convenient, even though the IRR is positive. And this is because a very simple reason. If the IRR is 13% and discount rate is 20%, this means that the investor, given the risk of a project, is expecting on this project a rate of return of 20%. So if this project is offering a rate of return that is the IRR of 13%, the investor will find this project unsatisfactory, because if we go back to the definition of the opportunity cost of capital, he could invest in a project having a similar risk and offering a return of 20%. So the 13% for a project having this kind of risk will be totally unsatisfactory. So I cannot say anything about the convenience of a project when I use the IRR method until I compare, and as we'll explain in detail in the following classes, the IRR with some measure of the discount rate that I think is appropriate for the project given its conditions of risk. Here I have an example of IRR calculation. We are using the same table we used before for the NPV calculation, so we are using the same assumption. We have first column where we report the year of the life of the project. Again, we have a project with a life of 5 years, and in year 0 where we make initial investment. So the operating cash flows will be the same, and we have minus 10,000 year 0, 3,500 year 1, 300 year 2, minus 1,000 year 3, 4,000 year 4, 5,000 year 5. So the IRR is calculated by using the formula we saw before. So we set the formula for calculating the NPV of these cash flows, and the results, we set the NPV equal to 0, and we solve this equation for the IRR, and the result is that the IRR is 12.69%. And this is an equation that can be either solved manually, but clearly it will be more complicated, it will take time. But it's an equation that can be easily solved using specific function in financial calculators or in financial Excel. So typically this is a result that I can obtain very easily using one of these standard solutions. Then the interesting thing that I would like that you notice is that the IRR calculation does not really depend on the choice I made about the discount factor. Here, in fact, we have the same calculation we had in the previous slide with the discount factors and the present values of the operating cash flows for different choices about the discount rate. So for the discount rate of 10% and 15%. Clearly, the fact that here in this column I discount the cash flows at a rate of 10%, and here I discount the cash flows at a rate of 15%, is not an implication for the calculation of the IRR, because the IRR is calculated on the operating cash flows before discounting. So there is no particular effect on the IRR calculation of using a different discount rate. But what matters instead is the decision about the project, because the IRR is equal to 12.69% and is given. So This is something that is not affected by risk considerations or consideration about the approved discount rate. But if I refer to the first hypothesis, where I have a discount rate equal to 10%, the project will be convenient because I will compare an IRR of 12.69% with a discount factor of 10%. So the IRR is higher than the discount factor. And according to the rule that we defined earlier, the project is convenient. But the decision convenient changes when we look at the second assumption, where I have a discount rate of 15%, where now the decision about the convenience will change. Is it changed when we consider the example the NPV? Because in this case, I have again an IRR of 12.69%, that does not change. But this time, the IRR has to be compared with higher discount rate that in particular is equal to 15%. So in this case, the IRR is lower than the discount rate. So this implies that the project, given the rules that we saw before, is not convenient anymore, and therefore should be rejected. So you see that even though the choice of a different discount rate does not affect the calculation of the IRR, that by definition does not depend on discount rate, will however change our final decision about the project, because with a discount rate of 10% we'll decide to realize the project, whereas with a discount rate of 15% we'll decide to reject the project. A final remark about this example and the IRR in general is that so far the IRR is being calculated for the total investment, so therefore it's being calculated on the basis of operating cash flows. The IRR, however, could be also calculated for equity investments, and the procedure will be exactly the same, with the same two differences that we already saw in the case of the calculation of the NPV to equity. First of all, the IRR for equity holders will be calculated on net cash flow to equity, not on operating cash flows. So this means that here in this column, instead of having OCF, we'll have NCF, let's say, for net cash flow to equity. The second difference is that once that I calculate the IRR in this way, the meaning is a bit different, because it's not the expected rate of return of the project for all the investors, but it's only the rate of return that the project is generating for the shareholders. So the meaning is different, and for this reason, also the rate of return that I choose as comparison has to be different, because this time I'm not comparing the IRR to equity with the discount factor for all the investment, but I will compare that with the rate of return expected by the shareholders, that in the case of the NPV formula we define as RE. So if we want to calculate the IRR to equity, we have to change the cash flow that are the basis for the calculation. So we'll take net cash flow to equity instead of operating cash flows. The IRR will have different meanings, because it will be the rate of return expected for shareholders and not for all the investors. And therefore we have to compare this IRR with a different discount rate that will be the rate of return that the shareholders expect on this project, not the rate of return that all the investors expect on this project. So now we'll look at another indicator, that is the modified IRR, that is a particular version of the IRR that tries to correct an assumption of the IRR, that is that it assumes that cash flows generated by a project during the life of the project are reinvested at the IRR. So the project is generating cash flows at different moments in time, as we know at this point. And when we calculate the IRR, we implicitly assuming that these cash flows that are generating before the end of the life of the project are reinvested until the end of the life of the project at the IRR. So now this assumption can be fine in some conditions, but there are some cases where the IRR of a project is very high, so it's quite unlikely that the cash flow that the project is generating over its life will be then reinvested at the same IRR of the project. It can happen that this is a particularly convenient project generating especially high returns, and so it will be implausible assuming that the cash flow will be reinvested in a project having the same characteristics. So in case we have high IRR and the assumption that we discussed is unplausible, we can calculate a modified IRR that can assume a different and realistic reinvestment rate for inflows. And moreover, the modified IRR, that is also defined MIRR, assumes a borrowing rate for outflows. So it basically assumes different rates for the inflows and the outflows. So its definition, the MIRR can be defined as the rate at which the future value of inflows equals the present value of outflow. So here we can see from this definition that in order to calculate the modified IRR, we have to estimate two values. One is the future value of inflows, that therefore, as we know at this point, will have to be calculating using the compounding procedure. So we have to compound all the inflows of the project to the end of the life of the project itself, whereas we have to discount all the outflows using, in this case, the borrowing rate. And then we'll find the IRR is the rate that basically makes equal the future value of inflows to the present value of outflows. So this definition is clearer if we look at this formula. So as you can see, the modified IRR can be defined as the ratio between two values that are p and n, raised to 1 divided by n minus 1. So this is basically the average rate of return that the project is generating on a yearly basis over the n years of its life. So we have to understand better what these p and n values are. So p is the future value of all the inflows. And in fact, here you have a summation that allows you to calculate the present value of the inflows, where in fact IF stands for inflows. So we have the summation of t, for t going from 0 to n of all the inflows. And each inflow is multiplied by its compounding factor, where rho is the reinvestment rate. So this reinvestment rate can be fixed in a flexible way as not to be equal to the IRR. So in the case the IRR is too high, we can choose a rho that is lower than the IRR. In this way we correct for this problem. And the compounding factor clearly refers to the year t, that is the year to which the inflow refers. So the formula of P allows us to compound all the cash flow to the end of the life of the project using some given raw reinvestment rate that can be fixed in a flexible way independently of the IRR. What is instead N? N is we are anticipating when we are giving the definition of the modified IRR is the present value of all the outflows that are generated in the life of the project, that these times are discounted using a borrowing rate as discount rate. So here we find that N is defined as the summation for t going from 0 to n, where n again is life of the project, of all the outflows multiplied by the relative discount factor, that this time is calculated dividing 1 by 1 plus beta raised to t, where beta is the borrowing rate and t again is the timing of the outflow. So in other words, we are first projecting all the cash flows to the end of the life of the project through compounding. Then we are discounting all the outflows of the project using the borrowing rate as discount rate. At this point, we can interpret the modified IRR is the rate of return that will allow to compound n for n years, and to get p is a result. Notwithstanding the correction that are applied when we calculate the modified IRR, the IRR is still some limitations that limit the possibility of using these dynamic indicators for the calculation of the value of a project in some particular cases. First of all, there are some particular projects that have no IRR. This happens, for example, for the project where there are non-outflows, all the cash flows are positive. In this case, the NPV will be never equal to 0, and so we have no IRR. But there are also cases where we have multiple IRRs. This happens when the NPV is equal to 0 for different values of the discount rate. This happens where typically you have more than one change in the sign of the cash flows over time. In this case, it can be problematic to interpret the results, because having multiple IRRs, we could be not sure about which IRR is the relevant one to understand the return of the project. But most importantly, as we'll analyze in more depth in the next classes, IRR could provide wrong indications in case of evaluation of mutually exclusive projects. In this case, it could happen that the IRR provides a positive indication as compared to the NPV. There are some particular cases where that we'll analyze where the IRR provides exactly a positive indication of the NPV in terms of the project that should be chosen among the mutually exclusive ones. So in these cases, what we'll see is that it's always better to use the NPV that defines exactly the value created by a project. So it's an objective indicator of the value created of a project, and therefore is the indicator on which we should rely in these cases. So we have to remember that IRR is surely a clear and useful and synthetic indicator of the return of a project, but not in all cases can be used given its limitations. And when it cannot be used, we have to go back to the NPV that is always a measure of the value created by a project. So at this point we look at the last dynamic indicators that we can use for the valuation of a project. This is defined as the net present value ratio, or NPVR. The net present value ratio is calculated as a ratio between the NPV of a project and what we define as present value of investment. What is present value of investment? Present value of investment is the present value of all the investment made for a project. So if the investment is concentrated just in year 0, so at the moment we start the project, then the present value of investment will be the same as the investment. But it can happen, as we saw in some of the examples we have seen together, that the investment is not concentrated just in year 0, but is divided into more years. So for example, you could have investment in year 0 and year 1. In this case, the present value of investment is equal to the investment at year 0 plus the present value of all the subsequent investment made after year 0. The net present value ratio is used in very specific circumstance. That is the case where we have to rank projects in presence of capital rationing. So what does it mean? It means that there can be situations where we have to make decisions among different projects, but we have limited resources. So we cannot invest more than a given amount, so we have financial constraint. And it can happen that, for example, we have more projects with positive NPV than those that we can fund given the initial financial constraints. So it can happen, for example, that we have 10 projects with a positive NPV. this requires a total investment of 2 million. We have only a financial budget of 1 million, so we have to select only some of these projects. So we have to rank them and then fund them until we terminate our budget. And in this case, the NPV ratio is an important one because it accounts not only for the NPV that the project is generating, but also for the investment required for the project, because it could happen that the 10 investments that they have to select present different initial investments, and so they absorb a different quantity of the scarce resources that in this case is the financial resource. So a project can have a higher NPV than other project, but can require a higher investment than other project, and eventually use most of the budget so that we will not have more space for other projects. So when we are evaluating and ranking projects of different initial size, of different investment, under conditions of capital constraints, we have to apply some kind of indicator that is different from the NPV, because if we apply the NPV indicator without accounting for the initial size of the project in terms of investment, we could make mistake in the allocation of our constrained financial budget. In order to understand better what error we could make in the allocation of financial resources to projects in case of capital rationing when we use the NPV, we can look at this very simple example that allows us to understand the utility of using the net present value ratio in situation when I have a capital constraint. In this particular case, we have a capital budget of 200. So this means that in this particular period, we cannot invest more than 200 in the available projects. And we have to choose among 4 projects here that are named Project 1, Project 2, Project 3, and Project 4. So these projects have a given NPV. So Project 1 is an NPV of 200, Project 2 is an NPV of 175, Project 3 is an NPV of 120, and Project 4 is an NPV of 75. So if we are choosing only based on the NPV, the ranking of the project will be the same as the name of the project. So we'll have Project 1, then Project 2, then Project 3, and then Project 4. So we should invest according to this ranking. However, this ranking does not account for the fact that these projects require an initial investment. So the PVI, that is the present value of investment, is different for each of these projects. And in particular, the project number 1 is, requires the double of the resources required by the other 3 projects. In fact, Project 1 is requiring an investment of 200, whereas Project 2, 3, and 4 are requiring an investment of 100 each. So the fact that the PVI changes across projects is relevant in this particular case, exactly because we have a capital budget and we cannot spend more than 200 in this project. So let's see what will happen if we decide to apply the NPV criterion to the choice of this project. So what will happen is that, as we were saying before, we'll start from Project 1, that is the one that is the highest NPV. This project, however, will require an immediate investment of 200. This means that we will complete all of our budget by investing in Project 1. And so we could not invest in neither of the other projects, and so we will get an NPV of 200 by investing only in Project 1. However, as we'll see in a second, this could be a wrong solution because it does not account for the fact that Project 1 is higher size and going to use the whole budget available for projects in that year. So in order to make a more correct decision here, we have to calculate the net present value ratio. is the ratio between the net present value and the present value of investment for each of the project, is appeared from the slide in the previous formula. So in the case of project 1, the net present value ratio is equal to 1 because you divide 200 by 200. In the case of project 2, net present value ratio is equal to 1.75, being equal to the ratio between 175 and 100. In the case of project 3, the NPVR is equal to 1.20, is equal to the ratio between 120 and 100. And finally, the project 4 is the lowest net present value ratio, equal to 0.75, that is given by the ratio between 75 and 100. So as we see, the ranking that we get based on the net present value ratio is different from the ranking that we will get from the NPV, because in this case, the project that is the highest ranking is project 2, because it has a net present value ratio of 1.75. Then project 3 follows with an NPVR of 1.20. Then project 1 is only served with a net present value ratio of 1. And again, project 4 is the last one with the lowest NPVR of 0.75. So at this point, I start ranking the project and funding the project according to the NPVR ranking. And so therefore, the first project that I fund is project 2. The funding project 2 would require an investment of 100. So I have still 100 available. And at this point, I can invest the remaining amount of money in project 3, so that I have, at this point, completed my budget. I won't invest instead in project 1, because having completed my budget with investment in project 3, at this point, I have no more money to invest in other projects. So if we adopt the NPV indicator to rank the project, we would invest only in project 1. Instead, if we use the net present value ratio, we will invest in project 2 and 3, so we get to complete different conclusions. And by the way, this is the correct conclusions, and we'll see in a moment why. In fact, if I invest only in project 1, I get a total NPV of 200, and that's the only NPV that I get because I have no budget to invest in other projects. On the contrary, if I invest in project 2 and 3 as suggested by the net present value ratio, I get a total net present value of 295 that is given by the sum of the NPV of project 2 and the NPV of project 3. So if I follow the net present value ratio indicators, I get a total NPV for the project that I will be able to fund that is much higher, is 295, than the NPV that I will get investing in the projects suggested by the NPV indicator, that in this case will be 200. So the optimal choice is to be based in this case on net present value ratio, not on the NPV. By the way, this is the only case where the NPV ratio is more useful than the NPV, because in other cases, clearly, the NPV will still say whether the project is convenient or not, and if it's valuable or not. So at this point, we have finished this class, and I thank you for your kind attention, and I will remind you that you can find additional materials on topics of this class on the course website.